Okay, welcome to our third note set in our fifth unit on A to D converters, with a little DAC stuff thrown in at the beginning. But now we're firmly looking at A to D converters. And if you remember, we already talked about how we need a probabilistic model for how the A to D converter affects the signal. And we argued or made some assumptions that we could model this as a particular type of sequence of random variables. And so then in the last note set, we kind of set aside our interest in A to D converters and just studied some of the important points that we'll need for characterizing random variables. And in this note set, we move on to random processes or random signals. Same thing. I got a couple readings here. Chapter 11 in Lathy's book. I don't know the exact title of the chapter, but it has the word or the phrase random processes in it. Another good source is this book by Monolakis, Engel, and Kogan. It's come out in a couple different editions and a couple different publishers, but pretty much any version of it should have this. And the version I have has this as chapter 3, but you're going to look for a chapter that has something about random variables, vectors, and sequences, and it's the sequences that we're doing here. So for discrete time, a random process is nothing more than a sequence of random variables. So that's where we're at. All the black type here is from the first slide of the last note set, where we were talking about how we need to come up with a model, probabilistic model for the noise that we're looking at. And now we're just extending this idea to a random process. So the things that we already talked about will be carried over into this note set, and then we'll apply all those ideas in the note set after this one. We'll start applying it to the actual characterization of the analog to digital converters. Okay, so what is a random process? Well, remember, a random variable, we said, was a bag full of numbers. And so if we're talking about the random variable that corresponds to the number on 2 dice, we saw that the bag contains the numbers 2 through 2, 3, 4, all the way out to 12 with I'm just going to draw it like this rather than a discrete function that it should be, but a triangular PMF. Okay, so that's a random variable. We got a bag full of numbers. Well, a random process, one way to think about it, is a bag full of functions. So remember, we're also talking about this being random signals. So if a random variable, we could think about renaming that random numbers. So if that's a bag full of numbers, a random signal is a bag full of possible signals. So here I show a bag full of possible signals. We're showing it in discrete time, but you could imagine some sort of bent wire and imagine a bag full of those. And I've got a dot, dot, dot here, and really it should go dot, 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 just keeps on going. There's infinitely many possibilities of those. So we got a bag full of numbers, a bag full of signals that together make up the concept of a random signal. And then there's a probabilistic mechanism. You reach into the bag and you're going to grab one of these pieces of wire. Which one? Which one is more likely? So there's going to be some probabilistic mechanism that will force you to pick one more likely than another one, perhaps. Okay, so that's one view. It's not the best view, but it is a logical extension of the idea of random variables to random signal. But here is another view. And this one is particularly easy and useful when we're talking about discrete time random processes. The study of continuous time random processes, which we will not need here, is a little bit funkier. But now for discrete time random processes, we're going to have an alternate view. So this is sort of like that, is it a wave or is it a particle view for light? Well, is it a bag full of signals, like we just talked about, or is it a whole bunch of bagfuls of numbers? That's conceptually harder to visualize, but analytically easier to deal with. So just think about a whole bunch of bagfuls of numbers. So that's what I'm showing here. There's my bag, and the dots in there are the numbers, and there is some probabilistic structure in there that inside each bag that tells us how those numbers are likely to be drawn. And remember, we talked about two random variables in the last set of notes, and we said we've got a bag for one random variable, bag for another random variable. They each have their individual mechanisms, but there was also a mechanism that connected those two mechanisms that accounted for any correlation between those two random variables. Well, we've got that going on here as well. And I just want to point out this zeta here, don't worry about that. That's something that they talk about in this book, to try to put a little firmer characterization on it. So let's not worry about that at this point. But so at time n0, we've just got this bag. At time n0 plus 1, we've got another bag that has all of these numbers in it with a probabilistic structure in it. Those two bags could have the same probabilistic structure in them, or they could be very different. And there's a connection, potentially, from instant to instant that says once you've selected a particular value at this instant of time, that changes the structure of how these values can be selected. So that's built into the mechanism. So we got a mechanism in each bag, connections between them, and there's no reason why we have to limit ourselves to just a connection between two adjacent ones. There could be a connection between those and a connection between those, and so on. So lots of correlation structure, and we're going to have to come to grips with how to characterize that. Okay, how do we characterize that? Well, we can do it with a PDF. But we can also do it with something called the autocorrelation function. So remember in the last note set, I said, the PDF tells us everything, joint PDF for 2. And then I said for 2 random variables, the joint PDF tells us everything, but the correlation, or the covariance, better way to say it, the covariance function between those 2 random variables tells us not as much as the joint PDF, but it does tell us something. So that's the same thing with the autocorrelation function for random signals. So we can say I've got a sequence of random variables, and we need a PDF at each instant of time. So that's going back here and saying at this time I need a PDF for that bag of numbers. I need a PDF for this bag of numbers. I need a PDF for this bag of numbers. Now, it may be the same PDF at every instant of time, but it doesn't have to be. But we will limit ourselves soon to that. Then the other thing is we need a joint PDF for all pairs, time n and a time k samples away. So going back to the previous page, we would need a PDF between this one and this one, and this one and this one, and this one and this one, and going backwards as well, this one and this one, and this one and this one, and so on and so on. And that would be, we would need that for everyone every point as a reference, right? So we would also need this one with this one and this one with this one. That's a ton of joint PDFs that we would need. So that is a lot of characterization. And we would need similarly the conditional PDFs. So again, going back, we would need this conditioned on this, and this bag conditioned on that, and this bag conditioned on that, and so on, and also conditioned on this one, and conditioned on that one, and so on and so on. So lots of joint PDF structure, lots of conditional PDF structure. Now, these all could change. They certainly are going to change as K changes, but they could also be different for each starting position. So lots and lots and lots of characterizations. Those two things, either one can be used to characterize, be more than what I'm about to say, but one thing is that we can look at those to see how likely is it that these 2 points are going to be alike or unalike. So think about weather. I'm going to use weather as a characterization here for a while. Think about weather. So let's pick N as August 15th. So how is the weather at August 15th correlate or jointly distributed with the weather, and let's just say temperature, to give it a random variable. Jointly distributed with August 16th and 17th and 18th and 14th and 13th. That's going to be the joint PDF anchored at 15, right? So by looking at that, we can get how likely the temperature will be at any pair of 15 with other dates. Likewise, we can do the same thing with conditional PDF. We can see that if I condition the, say, August 17th conditioned on August 15th, that's going to give me some sort of characterization of connection across these dates. So that's an awful lot of machinery that we have to nail down. We're interested in scenarios where we can simply rely on the PDF at each time and something called the autocorrelation function. And we're going to most generally define that this way. It's a function of n and k. So think about it. This is really just saying 2 different points, but I'm nailing it down in terms of a reference and a distance away from that reference point. So it's just the expected value of the product at time n and k samples away. And k can be positive or negative. So looking forward or backwards. We want this as a function of n and k. So this is capturing correlation. Now, when we looked at covariance, we subtracted off means. Here we're not subtracting off the mean. It turns out that this autocorrelation function without subtracting off the means is a little more convenient for working with the theory here. And furthermore, we're mostly going to be dealing with zero mean processes anyway, so it doesn't matter whether we subtract it off or not. So this is capturing some sort of correlation between 2 points, time n and a point k samples away. So that might change based upon n, right? So August 15th and 3 days away, 3 days in future. So August 15th is nailing down the n, and 3 days is nailing down the k. Well, the correlation between those 2 days might be different than, say, December 15th and 3 days in the future. that would mean that this autocorrelation function not only depends on the k, but it depends on the m, right? So this might also, if I were to change 15 and then 5 days in the future, that's going to change December 15th and 5 days in the future. That will change based upon k being 3 or 5, but it will also change based upon n in general. Okay, so that's the thing that we're talking about in general for autocorrelation function. It can depend on the point we're looking at as our reference and the distance that we're looking into the future or into the past. Now, that is more work than we're able to do most of the time, or more work than we need to do most of the time. So there is a simplification, a subclass of random signals or random processes that are called wide sense stationary processes, WSS. So we're going to limit ourselves to looking at that. Now, will this exactly describe the kinds of noises that we're interested in? Not perfectly, but close enough that it will give us some insight. So we just make this assumption that the noises we're interested in assessing will be wide sense stationary. And so this theoretical definition of wide sense stationary says a wide sense stationary process is a random process that has the following properties. So the first thing, this is the big one, is that the autocorrelation function, which we said originally depended on n and k, our reference point and the distance away that we're looking, now depends only on k. The n dependence goes away. So no matter where I pick my reference, August 15th, December 15th, the connection between temperatures on those on a day, k days away from each of those two dates will be the same. Now that does not hold for weather. Weather is not wide sense stationary, but other things are well modeled by wide sense stationary processes. So the things we're interested in are well modeled by this. Another thing we need in order for a process to be wide sense stationary is you take the expected value of each bag. So what is the mean of each bag? It's a constant, doesn't change with time. That also does not hold true for temperature, right? Because the average temperature or the expected value of the temperature in August is not the same as the expected value for the temperature in December, right? Maybe 80 versus 80 degrees Fahrenheit versus 25 degrees Fahrenheit, at least where I live. So not wide sense stationary for temperature at a given position. Okay. The next thing, so these are two important characterizations. The next thing is that the PDF, the single PDF, the PDF of the bag at time n doesn't change with n. So we go back and we say, so not only is the mean at each instant of time. So I look at this bag, the expected value of that bag, the expected value of this bag, the expected value of that bag. The expected value of every bag is the same, and the whole PDF of each bag is the same. So the PDF doesn't change with time. Nice. So that means each bag has exactly the same mechanism inside it, controlling the likelihood of picking. And this part tells us that the linkage between mechanisms, it doesn't matter where those 2 points are, August or December, it just matters how far apart they are. Nice. So let's look at some impacts of these conditions that are a definition of a wide sense stationary process. Well, the first thing is if we let k be equal to 0, we get x squared of n, and x squared of n, since it does not depend on n, will be a constant. And so this is the average power, right? This looks like power. Think about a voltage squared divided by R. Well, just imagine that we have this fictitious resistor of 1 ohm. So this is like at least proportional to the power of that signal if it's a voltage. So we call that the average power. Average because we're taking the expected value of that. And so the average power doesn't fluctuate with time. Nice. Another thing is that the variance is constant. So if we look at the variance, remember at each instant of time, we take that random variable minus its mean, square it, take the expected value. Well, if you manipulate this, square things out, do some manipulation, you can show that it boils down to the autocorrelation function evaluated at k equal to 0, which we said was a constant, minus the square of the mean, which is a constant. So this thing must also be constant. So the variance is constant. Now, notice the difference between those two things. The only difference is whether we subtract off the mean or not. So keep that in mind. So the power is equal to the variance when the mean is equal to 0, because when the mean is equal to 0, that goes away, and variance is the same as the average power. So all the processes that we're going to deal with will be zero mean. So we'll get a little bit loose with making this connection between power and variance, but in general, you might not want to get that loose. So we're going to use two things to characterize our wide-sense stationary random process, or random signals, or random noise, whatever term you want to use to describe that. We're going to say, oh, one PDF, whatever it is, it'll be the same at every instant of time, and an autocorrelation function that only is a function of the offset k. And we'll call that k variable the lag, right? How far one point lags from the other. So that's just a term that people throw around for discussing these things. So we've defined this autocorrelation function. We can plot it as a function of k, and it'll show us the correlation between any two pairs separated by that value of k. That's pretty much what it tells us. It tells us how the process is correlated at different points. But really, what matters is not where in a global setting those 2 points are, only how far apart they are. So it doesn't matter if we're talking about August 15th to August 18th or December 15th to December 18th. That spacing is the same, so the correlation will be the same. It doesn't really work for temperature. Now, remember that we're looking at the expected value of the product of these two things. So if those two things are highly likely to have the same sign, then the product's average or expected value will be positive. So if they're both positive, the product is positive. If they're both negative, the product is negative. Go back and look at how we introduced the concept of covariance, and we talked about correlation and things like that. If, for a given value of k, these two things are highly likely to have opposite signs, then this product is highly likely to be negative. So the expected value of that product will be negative. And the autocorrelation function at that lag k will be negative. And for a k value where this product is just as likely to be positive as it is to be negative, so that those things cancel each other out when you average them out, the autocorrelation function should take on a value of 0. So we're going to explore this view in the next two examples, and we'll see how by looking at the autocorrelation function, we can get a feeling for how rough and ragged the signals that will arise as part of this process will be. So, hey, there for a second, we went back to that bag full of signals viewpoint. So, but here we're analyzing it all from sequence of bags viewpoint. We get the insight using these tools, but then we can say, oh, if that's true, then when I start pulling out full signals, right? Remember, is light a wave? Is it a particle? Yeah, it's both. Are we using, can we say a random signal is a sequence of bags, or is it a bag of signals? We can think about it either way at any time we want. So the second thing that this tells us about is the power of the process. So if we take Rx of 0, remember we're setting k equal to 0, so we're getting the expected value of the square of the signal at time n, which we said is constant, does not depend on the value of n, and we define that to be the average power of the process. And we'll just give that the symbol p sub x. And again, that's constant for a wide sense stationary process. So the power doesn't change with time. Well, if we look at this, if we do a little bit of analysis, I didn't go through the steps, but we can also show that the variance, so remember the variance looks like this, but in each term we have to subtract off the mean. So if we analyze that, we can show that the variance ends up being the autocorrelation function. Well, that's the power, evaluated as 0, that's the power, minus the square of the mean. So I've just written that out explicitly, talking about the power. So rewrite that. Put px here and swing this over to the other side. So now I've got that the power of the process has two things that contribute to it. One is the variance. Remember, that has to do with the amount of fluctuation around the mean. And then the other thing is, how big is the mean squared? So when the mean is 0, again, as we just said a minute ago, the power and the variance are one and the same. But when the mean is not 0, we think about there being an AC power. That's the fluctuation around the mean. And then there's like a DC power. That's that constant mean that if it's a large value, positive or negative, that gets squared, it's a large DC power. So, in our studies here, that will be 0, and we don't have to make a big distinction about that. But in other applications, we may need to keep that in mind. Now, here's an example, and it's a very relevant example. This is a good model for our noise from a analog to digital converter. We alluded in the first note set in this unit that we would make the assumption that our error from the quantization process or action would be uncorrelated or independent from sample to sample, and we said that was a white random signal. So let's define what we mean by a discrete time white noise. So let x of n be a sequence, okay, we're back to that sequence of bags model, a sequence of 0 mean random variables. So we're making a random process or a random signal or a random noise from that sequence of bags viewpoint. And we're going to say each random variable in the sequence, well, it has a constant mean of 0, has a constant variance, and this is the key thing, independent from all others. So if we put all these things together, what we can find from that is expected value of this product. Well, that's the definition of the autocorrelation function if this is wide sense stationary. We haven't said anything about the PDF here, notice, but we're saying that the mean is constant, the variance is constant, and I suppose I should go further and say, and the PDF is constant, but from this definition, especially the independence part, we can then show that this has to be equal to 0 as long as k is not equal to 0. That's because any two bags in the sequence are independent from each other, and then we can say that this expected value turns into a product of the expected values. That's a property of independence. And each of those go to 0. And that's where we get that. But if we pick k not equal to 0, so or k equal to 0, so that's true when k is not equal to 0. But what happens when k is equal to 0? Well, now we get the expected value. Well, I guess I can get rid of this too. In that case, we get the expected value of x squared. And that's just the variance. So it's not 0 for k equal to 0. So now we can write this. We can take these ideas and put them into one expression. The autocorrelation function as a function of k is this. There's no n on the right side, so this does not depend on n. Nice. Wide sense stationary. So this defines a wide sense stationary process that we call white noise, or an uncorrelated process is another name for that. Physically, what does this mean? It means that by observing the process at any time, that observation gives me no insight into how likely it is for the process at other times to take on certain values other than just abiding by its individual PDF. So it breaks those links between the bags. So each bag has its own solo mechanism, but there's no cross mechanism between bags. That's what we've got going here. It's like taking a die and rolling it and getting a number. Now you pick up that die and you roll it again. So that second roll is the same bag because it's the same die. I roll it again. But despite the gambler's fallacy, look that up if you want, the previous, no matter how many previous rolls I've had, if I haven't had a single occurrence of 2, my current roll, it's 2 is no more likely than it was on any of the other rolls because it's a white noise. That's the concept. Okay, so what did we just show? We showed that the autocorrelation function for this white noise looks like this. For any k that's not 0, the correlation is 0. And when k is equal to 0, the result is the variance. And I had a sigma sub x here. I should have a sigma sub x there. I guess I should. Yeah, I do have a sigma sub x there. So I should have fixed this. Should have put a sigma x there. Didn't do that. So what would one of these things look like? Let's go back to the bag full of signals. When I pull a signal out of that bag full of signals, I call that resulting signal a realization of this zero mean white noise. So that bag full of signals is a bag full of possible quote-unquote realizations. Don't get hung up on the terms. It's just a name that's being used. And we can see how from this sequence of bags viewpoint, every single one of those signals or those realizations should have this very rapid fluctuation characteristic because from sample to sample, this signal is uncorrelated. That's the concept of a white noise. Now, notice that nothing was said about what the PDF is, other than I said, oh, I should have said that the PDF doesn't change with time. That's one thing that I should have specified. But it doesn't matter if that PDF is uniform, Gaussian, Cauchy, whatever. It doesn't matter. So I'm going to show you a picture. This is from one of my favorite books. I mentioned it at the beginning of this video. Great picture here showing three different realizations or three different processes. And this is a sample sequence from the first one, sample sequence from the second one, and a sample sequence from the third one. So sample sequence is another name for realization. So again, we're slipping back into the model or the view of, oh, is it a wave or is it a particle? Oh, is it a bag full of signals or a sequence of bags? Well, we analyzed this with the sequence of bags viewpoint, and now we're slipping back for a moment to think about it as a bag full of signals. So here's one of those signals for this process. There's its PDF, a uniform PDF. A different bag full of signals has Gaussian PDF at each instant of time. A different process, Cauchy PDF at each instant of time. And you can see each one of these realizations or sample sequences from their respective process, their respective signal bag, has that sample to sample roughness, willy-nilly from sample to sample. Sorry to get theoretically technical with you there. Willy-nilly is is not a theoretical probability term, but it tells you what I'm talking about. But what's different? The PDF is different. So this looks different from this one, and it looks different from this one, but still white noises. So look, the PDF is telling me the value at any instant of time, what values are likely or unlikely. Since this has heavy tails, I'm likely to get more outliers. This has less heavy tails, so it doesn't go as far out. And this clearly just clamps things right down. The correlation tells us something about how the thing behaves sample to sample. That gives us this raggedness. So we need both of those. PDF to characterize how likely different values are at each instant of time, and an autocorrelation function to tell us how connected values are from time to time to time. That's what we use these for. Now, here's another example. Hopefully this will give some further insight to this. So here's an autocorrelation function. It's the white noise autocorrelation function. So I'm saying that's the process that I'm putting into this simple 2-tap FIR discrete time filter. Here's the input sample, random process, one sample function. Okay, back to the bag of signals viewpoint. Pull one out of the bag that corresponds to this random process. It might look like that. It's uncorrelated sample to sample, so it's a white noise. Now, I'm going to put that process into a filter. What does that mean? Oh, remember when we talked about adding to random variables to get a new random variable? And I said you take everything inside the one random variables bag and you add it with every possible combination to the values inside the other random variables bag to create a new bag of values. Well, I'm going to take every sample function in this process bag. So now I'm thinking bag full of signals view. I'm going to shove every single one through this filter, and out comes, for each one that went in, out comes an output. And I'm going to put those into the bag, the output bag. So I've got a bag of signals here, and I've got a bag of signals here. Now let's step away from the bag of signals view and think about this output process from the sequence of bags viewpoint. How do we analyze that? Well, let's think about it. Y of 0 will be equal to x of, let's start with 1. Y of 1 will be x of 1 plus x of 0. And y of 2 will be equal to x of 2 plus x of 1. And y of 3 will be equal to x of 3 plus x of 2. Now, remember, these are random variables. That's the random variable at instant 1. This is the random variable at instant 0. So the output random variable at instant 1 is just a sum of two random variables. Okay, so let's look at this. How are these two random variables correlated? Well, look, whatever value this one takes on here, it's going to have the same value here. It doesn't change because as I take one sample function and run it through my filter, those will always be connected like that. So there is the connection between the two bags for those. And then I have a connection here. So there's a connection between those two bags. But do I have a connection between those two bags? Nope. 1 and 0, 3 and 2. No common value between them. So what that tells me is that I expect correlation one sample apart, but not two samples apart. So one sample apart, yes. One sample apart, yes. Two samples apart, no correlation. So it should be no surprise. And if we analyze this, we'd be able to find out, and I'll give you some simple equations to use to do this, but we could do it using the ideas that I just sketched out there, the expressions. But now here is our one sample away in both directions correlation, but two or more samples apart, zero correlation between them. And here's, if I had this sample function going in, and this is the sample function that comes out. So I literally in MATLAB just took this actual sample function, ran it through this filter, and there's the sample function. But for every sample function that goes in here, I'm going to have some sample function coming out here. Every input sample function is going to look like white noise. It's going to be jagged, uncorrelated sample to sample. But now the output sample functions have to show this one sample correlation. So it's a little bit smoother. See how this is smoother than this? It's like weather is correlated from, or the temperature is correlated from day to day. And let's just say it's the high temperature, right? If it's 90-degree high today, it's highly likely that I'm going to have a 90-degree-ish high tomorrow. But there's going to be a point where it breaks. So that's this idea here. So this is a 2-day correlation. Okay. And that came from this discrete time filter. So one thing we're seeing here, a big idea, is that if you start with a white noise and run it through a filter, that filter changes the correlation structure of the output sample or the output process. Okay, let's do this further. Now I've got 5 ones. And if I wrote this all out, you would see that for k equal to 1, 2, 3, 4, for spacing of 4 samples now, we have correlation, and therefore also for 3 and 2 and 1. So now my autocorrelation function is much broader, and here's the output random process, one sample function. It's even more correlated. So now we're starting to get long runs that show similarity of values. And let's continue this. Now I've bumped this out I'm just using MATLAB terminology here. Now I've got a filter of 10 ones, much broader autocorrelation function. Oh, now look at this. A much smoother process coming out with long runs of similar values. Still can fluctuate, but because it's not certainty, it's just correlation. And did I take it one step further? Yes, 15 ones. Now look, really long runs of similar values. Much broader autocorrelation function. And why are these triangles? We'll see. We'll see that in a little bit. We'll come back to that. So the big thing I want you to get out of this is by looking at the autocorrelation function, and for this case, we see that there's a fair amount of correlation over quite a far distance. So that means things spaced 10-ish samples apart are going to be highly correlated with each other. That leads to a smoother process when we see a broad autocorrelation function. And that leads us to this big insight. So it's less about filtering, although that is an important concept. The insight I want you to see here is the shape of the autocorrelation function's impact on how smooth the sample functions of the process are. So if I have a narrow autocorrelation function, I'm going to have rapid fluctuations. We saw that at the start of this little example. This is the extreme case. Narrowest possible autocorrelation function, most rapid fluctuation. A little bit wider, but still really narrow. A little bit smoother, but still pretty rapid. All the way up to a very broad, long distance correlation, much smoother, slower fluctuation. And so that's what we're seeing here. A broad autocorrelation function leads to a process whose sample functions are smoother. They have slower fluctuations across time. Okay, that's autocorrelation function. Now we're going to go to power spectral density. And if you remember, in note set 1 of this unit, I said autocorrelation function or power spectral density. They both tell you the same information, just in different ways. So PSD, don't get that confused with PDF, probability density function. These are different things. Remember the probability density function, going back a few slides here, when we were looking at the uniform versus Gaussian versus Cauchy. That doesn't affect how things are smooth. It just affects the range of values that are likely to happen. So that's what the PDF is telling us. The autocorrelation function and the power spectral density, or the power spectral density, is telling us how wildly it fluctuates from sample to sample. So it's right there in the name. It's about power. So I've got a power here, the power of the process. It's about the spectrum. So it's got frequency involved. And it's about a density. So there's going to be some integration to find an area under a curve to give the power. And so this is just by definition, or one way to define the power spectral density. So this is the power spectral density here, and I'm integrating it from minus pi to pi. Yeah, it's discrete time frequency, so minus pi to pi is what I need. And outside of that, we'll see in just a little bit that it does just repeat periodically. Okay, so from the power spectral density, I can get the power of the process. Remember, we could get the power from the autocorrelation function as well, right? Take the autocorrelation function, evaluate it at 0, and that gives us the power of the process also. So here's a picture of possible power spectral density. And I'm showing it from minus pi to pi, but this is discrete time frequency. So out here it would repeat. I didn't do a very good job drawing it, but this would be a periodic thing. These would look the same as that. So there's a nice little picture of it. It's power, so it can't be negative. So I'm showing it being strictly non-negative. And it's a density. So if I wanted to know how much power is there between two frequencies, now we're doing the complex frequency idea, complex sinusoid view. So we have positive and negative frequencies. Both of these contribute to the actual physical sinusoid. So we need to count them both. So we find the area under here. We find the area under here. That is the power in the band omega 1 to omega 2. That's kind of interesting. We can say, oh, I've got a random noise. How much of its power is focused in this range of frequencies? How much of it is here? And our signal might be stronger. Our desired signal might be stronger in certain bands and weaker in other bands. So we might want to see how the strength of the signal in a band corresponds to the strength or power of the noise in a band. Okay. So that was for discrete time processes, and we were looking at it in terms of the discrete time frequency, omega, in radians per sample. That's the unit. And when we're doing audio, we almost always like to tie things back to the physical real world. So even though I'm inside discrete time processing, I want to tie it back and say what's going on equivalently relative to frequency in hertz. So let's make that change. We could remember the formula for it, or we could just deduce it. Remember, Fs over 2 hertz corresponds to pi radians per sample. So that's the connection. And once you have that, you can deduce either of those two relationships. Here we are using Fs, and here we're using its reciprocal, capital T. Now we can make a change of variables. So we started off with this by definition. We're going to change variables, so we can change this to a function of f. We can change the omega to f. We can change the differential. The differential will get changed to that. We can change the limits of integration, and then just do a little bit of manipulation and define a new thing, right? The two pi's end up canceling with each other, and we define a new thing. We'll call it S sub x tilde. Just made that up. That's not a standard notation. Now we can look at this and see, oh, this thing clearly has units of watts, since I'm getting that in watts. And so this has to be watts per hertz to cancel with the hertz of my df. So this new definition, so it's the power spectral density of the discrete time process interpreted along the hertz axis. So that will have units of watts per hertz. And we can also interpret this thing, but we have to include the over 2 pi. That's going to have units of watts per radians per sample. So just two different ways to think about it. And I'd just like to point out, we're not going to fuss too much with that, whether we put a tilde on it or not. If I put an F there, you'll know that I'm really dealing with the normalized version to have it be appropriate versus F. So we're not going to make a big distinction about that. Okay, Wiener and Khinchin, two huge names in the theory of random signals. Wiener was in the United States. Khinchin was in the Soviet Union. After World War II, they were each working through these ideas. I think it's safe to say they didn't talk. Right? The U.S., even though they were allies with the Soviet Union during World War II, after World War II, they didn't really cooperate, and we got into the Cold War and so on. So they both worked this out, and it's nice that we now honor both of them with the fact that they both independently came up with this relationship. And what they showed, and of course they were doing this originally for continuous time, but they also worked out discrete time versions of this. If we have a wide sense stationary process that has that as its autocorrelation function and that as its power spectral density, they showed that those two things form a DTFT pair. So you've got the autocorrelation function, take its DTFT, and you've got the power spectral density, or vice versa. If you know what the power spectral density is, take the inverse DTFT and you have the autocorrelation function. So now I've just written that out explicitly. This is the form for taking the DTFT, and this is the expression for taking the inverse DTFT. Nice. We can also see this idea that it is a power spectral density, right? If I say, well, the power is the autocorrelation function evaluated at 0, that makes this go to 0, makes that go to 1, and there we have it. That's our definition of the power spectral density's contribution to compute the power. So this just gives us a new way of thinking. So we can think about the process in terms of its autocorrelation function, but we can also think about it in terms of its power spectral density. So we've already seen the autocorrelation function gives us, among other things, some insight into how rapidly we expect the process to fluctuate. Well, the power spectral density should give us that as well, because if I can get one from the other, anything I can see in this, I should be able to find a way to see that in the power spectral density. So let's revisit our white noise case. Discrete time zero mean white noise, we saw had this as its powers or its autocorrelation function. And in some sense, we can clearly see that must be the narrowest possible autocorrelation function. How can you make that narrower without just making that equal to 0, which means that the process has no variance? So doesn't make sense. That would just be the number 0, or the signal 0 in the bag. That's the only thing in there for that process. So this is the narrowest autocorrelation function that we can get. Remember, narrow autocorrelation function means the sample functions are going to be wildly, willy-nilly fluctuating from sample to sample. Well, what's the power spectral density? Complements of Wiener and Khinchin, we can find that. Just take the DTFT of this delta function. Well, the DTFT of a delta function is 1, so we get the sigma x squared out in front. So that is the value for all omega. Now, it's a DTFT, so we really should only look from minus pi to pi. So there it is. Look from minus pi to pi and you'll see it, but I've also drawn it outside of that. Remember, it just repeats periodically. So no surprise there that it's just going to end up looking like a straight line that goes on forever. But in reality, we're really just looking from minus pi to pi. Everything out here is just a spectral replica. So in some sense, I put this in quotes. I didn't put quotes here because that truly is the narrowest. But this is sort of like the broadest power spectral density. The first time I used this idea, a student said, well, what if I had a power spectral density that did this kind of thing? Wouldn't that be considered broader? I was like, okay, yeah, I'll put some quotes around it. So, but clearly this is broader than this. I'm sorry, broader than something that might look like this, right? Okay. So it's broad in some sense. So it's flat. White process. Why do we call it a white process? Because its power is spread uniformly over all frequencies, like white light. I kept referring to the, is it a wave or is it a particle? Now we're right back to light again. White light has its power spread uniformly over all colors combined together. So that's why we call it white light or white noise. Okay. Here I show, again, just the area between minus pi to pi, but I've now converted this into the F. So now it's going minus Fs over 2 to Fs over 2. And if I know the area of that must be equal to the power, which is sigma x squared, which I can get from up there. So since it's zero mean, I can deduce what the level of this is going to be. The level would be sigma squared x, that's the area that I have to have, divided by the width of this will give me the height. And I can rewrite that as capital T times the variance. So that's white noise, and that's why we call it white noise. Now, remember back a few slides, we filtered random processes, and we saw that filter spreads the correlation out. I mean, the filters we looked at do. There are some that don't necessarily do that. But that was the view that we were looking at. This nice, simple, low-pass FIR filter. Yeah, that's a very, very simple low-pass filter. If you look at its frequency response, you'll find that it looks something like this. That's its frequency response. So attenuates at the high frequencies. Okay, well, if I put in white noise at the beginning, here's the characterization, autocorrelation function, and power spectral density of the input. Now, we already looked at the power spectral density for that. It's nice and flat. What comes out of this? What's the power spectral density for the output process? Well, I showed you a plot of this when we did those examples earlier, but with a little bit of analysis, you can show that the output process has this as its autocorrelation function. Remember, that was what we saw. It has a delta there and a little delta there and then zeros elsewhere. That's what we saw before. So this is the center one to the right, one to the left. Okay. If we take the DTFT of this, we can use our DTFT properties. Delta transforms to 1. So I get the 2. The sigma squared stays out in front. This with the time shift property transforms to 1 times e to the minus j omega. This one, e to the plus j omega. Oh, there's an Euler waiting to happen right there. So let's combine that into Euler, do a little bit of algebra, and we get something that looks like that. And there it is. So, hey, remember I said that this filter was a low-pass filter? Well, look what it's doing. The power at the high frequencies at the output is now less than the power at the low frequencies. So in some sense, this has attenuated power at the low frequency or high frequencies relative to the power at the low frequencies. And again, we just look from minus pi to pi. This is a replica, and dot, 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 dot. Okay, nice. So the filter reshapes the power spectral density. And in this case, it suppresses the power at high frequencies because the filter is a low-pass filter. If I had a high-pass filter, it would be the reverse. It would suppress power at the low frequencies and let power at the high frequencies through. Okay. So here's our big picture, expanded. So remember we said a narrow autocorrelation function. We argued earlier that that should give us less correlation from sample to sample, and we saw that that gives us rapid fluctuations in our process. But now a narrow autocorrelation function should transform to a broad power spectral density, right? Because Fourier transform of something narrow gives me something broad, and a broad power spectral density means more power at high frequencies, and powerful high frequencies mean rapid fluctuations. So either way, correlation function, power spectral density, I can figure out what I expect the process to be doing fluctuation-wise. Now, on the other hand, so that was a narrow autocorrelation. A broad autocorrelation function, that shows more correlation from sample to sample, which leads to slow fluctuations. Or the broad autocorrelation function gives a narrow power spectral density. So now more energy or more power is concentrated at slowly moving low frequencies and less power at the high frequencies. And so we get slow fluctuations. So again, either way we view it. So lots of different ways. And I'm saying go back and look at those results for those filtered random processes back a few charts. And our final slide in this note set ties this together with a nice theoretical characterization. We could prove this if we wanted to, and maybe you did in a prior course, but I'm just going to state them. So if we're looking at random processes, and technically we should be talking about wide sense stationary random processes. Everything we're talking about looks that way. So I've got that there. So here is a discrete time, linear time invariant system with an impulse response h of n and a frequency response h of omega. And into that system, I'm going to put a wide sense stationary process. So remember, bag full of signals. Every one of those signals goes into the filter, gets filtered by H, and comes out as a realization of the output process. So I've got a bag of output processes. Okay, let's switch to the sequence of bags viewpoint. At each instant of time, the input's mean is constant. Its autocorrelation function, looking at correlation from bag to bag to bag, will have some function, whatever it is, and the power spectral density will be the DTFT of that autocorrelation function. Now, I want to know what are these three things for the output process. And they should be an interaction between these three things and the system's characterization. And in fact, it is. So look, what's the mean of the output? It's the input mean times, having a hard time there, times the DC gain of the system. So the frequency response evaluated at a frequency of 0 gives how a DC component goes through the system. And that is the DC component of the process. Okay, now the output's autocorrelation function is the input's autocorrelation function convolved once with a time-reversed version of the impulse, and then that result convolved with the impulse response. So that makes sense. This is a second-order characterization of the process, meaning it's an expected value of the process at a time times the process at another time. Second order. It's in there twice. So it makes sense that the impulse response should be involved twice. Now, I want to use this to point out how I knew this result way back here. So I got to go back a little ways, so bear with me here. Here we go. How did I know? We'll do it with this slide here. How did I know that when I had this filter of all ones that it was going to end up being a triangle when the input was a delta or was a white noise? So remember the autocorrelation function in, let me back up. Let me just talk about this one. 5 ones, okay? So a delta function is the autocorrelation function in, and now that's going to get convolved with this thing twice, one flipped. So if I take 1, 1, 1, 1, 1 convolved with 1, 1, 1, 1, 1, this is my reference at 0. If I convolve those two things, I'll get a triangle, which then convolved with this just gives me that triangle back. That's why I get a triangle here. It comes from, let me see if I can get tricky here. Yes, it comes from this result. So for that all ones filter, this gives the triangle convolved with the white noise's delta function, just replicates that triangle. And so the output autocorrelation function is a triangle. Now, let's look at power spectral density characterization. The output power spectral density is the input power spectral density, not times the frequency response magnitude, but magnitude squared. Again, second order thing, so I expect the frequency response to show up in a second order way. But for a white noise, this was flat. And when I put it through that all ones filter, I get some sort of sync-like thing that's going to end up getting squared and then multiplied by this, but it'll be a low pass filter effect. So everything makes sense. So hopefully this will provide you with some more insight. You've probably seen these ideas before, but maybe just in a panic. I just need to do this for this exam and this homework. I don't really understand what I'm doing. Hopefully this time it provides you with some insight to what these things are for, what they're good for, and what they're able to show you for insight. So now we're done with the esoteric abstract characterizations of random noise, and we are now going to embark on using these tools to characterize the effect of an analog to digital converter. We're going to model that round off noise or that round off effect, that rounding error as an additive noise, and see if we can characterize its PDF, its autocorrelation function, its power spectral density, things like that. And then that will allow us to think about how to make sure the ADC does not have an excessive effect on our audio. So that's what's coming up. I hope that I'll see you there.